Hi, I'm Ryan Nickel, CTO at DSA Ocean, and today I want to talk about the influence of vessel trim on hydrodynamics and seakeeping in the ship motion analysis process. So I have three projects here. What I've done is set up the generic fishing vessel in a couple of different configurations. We have the neutral trim configuration here, another configuration I've called stern trim where it's bow down, stern up in the air a little bit, and then the other way around where we have what I've called the bow trim where the bow's up out of the water, stern's quite a fair bit more in the water. And I've just gone through a couple of analysis cases to show what the differences are. So when might you want to do this, operationally, there might be some changes to the trim of the vessel depending on the loadout, the operational condition, and this is giving you an idea of how you can go about checking the effects of this. Now, what I found is because the trim is a fundamental parameter that's checked in each of the applications, because it's really easy to get confused when you're going through the process of setting up the ship model, calculating the hydrodynamics, evaluating the motion in the seaway. It's a fundamental parameter that's going to show up in all of these, and it's really easy to get confused. Some things are really quick and easy to do for a sensitivity study. The fundamental parameters are a little tricky. So what I recommend and what I found easy to do is just make a copy of the folder and go through the process of updating the trim value across the board in all the applications, and then you don't get confused. So when you set it up in the first step is in panel hull, you'll see right away when you change the trim, you'll get that visual feedback right away of like what does it look like um, as you change the trim angle. And this is the neutral trim configuration here in panel hull. So I've gone through and calculated all the hydrodynamics. And the other cases are um, a difference of 2 degrees only, plus or minus 2 degrees. So the first thing we'll do is we'll just take a quick look at the radiation values here. So these are the wave radiation values. And maybe the number one thing you might see a difference in is pitch damping. So if we just take a quick peek at the peak pitch added mass values, you see non-dimensionalized, we're getting like 1.18 for neutral, and then that's changed quite a bit to 0.9 in the stern trim case, and the bow trim case here it's 1.1. So it's there's some variation there. Enough to make me think that yeah, you might expect to see quite a bit of a difference in the ship motion results, but that's something that is usually the most clear about what will happen. So what I've done is I've taken each of these models and run a ship motion analysis in a 3-meter 7-second peak period sea state with it's not long crested, it's got some spreading, but I mean it's the same for all of them to just be representative. Now when we look at the same conditions and the same motion values, what we're looking at here is all of the ship motions. 180 degrees is head C, 90 degrees is beam C, and 0 degrees is following C for all the different motions: surge, sway, heave, roll, pitch, and so on. So because we're playing with the trim, I kind of expect to see the most variation in pitch, but we'll check some other things as well. And so for the neutral trim case here, in a head C, we see RMS 5 degrees, and we expect to see sort of the biggest pitch motions in head and following C. Okay, so how does it change when we start messing with the trim? Well, 6.9, it's getting close to 7. Like that's quite a big change in the pitch motion as a result of only a 2-degree change in trim. So that's interesting. And then in the other case here with the bow trim, it's gone down a little bit, 4.6. So you can get quite a big variation. And this is the RMS, not the maximums, but you're getting quite a big variation. And of course, we start to see bigger in head C versus following C, and the other way around when it's trimmed the other way. So the other thing that's kind of interesting here is when you look at the roll motions, we have 10 degrees RMS roll. This is getting pretty close to the roll natural period at 7 seconds, so that, we're expecting to see kind of a lot of roll here. And it starts to go down a little bit, and then up depending on how it's trimmed as well. So anyway, the main thing I wanted to highlight was how to use the structure of the program to evaluate it, and certainly it's worthwhile to get a sense of how they might vary and what the worst case scenario might be. And of course, all of these motions are going to affect the accelerations elsewhere on the rest of the ship, so it's well worth looking into. All right, that's all I wanted to check in with today. Thanks for watching. I'll see you online.